Hello and welcome to the new episode of the Gene Therapy Insights podcast. Today I have a very special guest, and I know it's been a while, but this episode will be none less than exciting. My guest is Matthew Scholz. Matt is a serial entrepreneur with a background in computer science and immunology. He's bridging the best of the fields of physics, computing, genetics, and medicine. He's on the forefront of anti-aging technologies and non-ordinary approaches to rare disease gene therapies. He is the chief executive officer and co-founder of Oisín Bio, a company focused on mitigating the senolytic technology to combat age-related diseases with a gene-delivered technology based on proteo-lipid vehicles. We'll get into that. Matt is also the founder of Immusoft, a biotech developing a breakthrough technology that turns patients' B cells into miniature drug factories. He is a co-founder and board director of Sigma Genetics, a company building a non-invasive device that can deliver charged molecules such as DNA, RNA, and proteins into patient cells. He's a CEO and board member of OncoSenX, the company developing transient gene therapies designed for solid tumors. And lastly, he's a co-founder and chief technical officer of Aegis, a company that works to protect human health from infectious diseases through Fusogenix technology. I know that's been a lot, so I'm very excited to bring you our conversation where Matt shares his fascination with programming and immunology, especially the concept of immune memory and the creation of the immune software, hence Immusoft, where B cells are reprogrammed to become enzyme-producing factories. Matt discusses the MPS1 or mucopolysaccharidosis type 1 program and the work that it took to dose the first patient with this detrimental disease. We'll lead the discussion into the information theory of aging, treating genetic disease as misinformation, hence its correction. We glaze over the transposon systems and the mysteries of retroviral DNA, and we get into viral versus non-viral approaches to gene therapy. You'll be delighted to learn about the progress being done in follistatin gene therapy for enhancing muscle growth, senolytic gene therapy to tackle age-related diseases, and the continuous and ever-changing views that FDA takes on such uncharted territories. I am thrilled to bring you this episode, and I hope it amuses you with new ideas as much as it did to me. All right, Matthew Scholz, welcome to the Gene Therapy Insights podcast. It is so awesome to have you here with us. I'm super excited for our conversation, and I already told my audience that you are just a fascinating person who have founded several companies, and the approaches that you've taken are of so much interest and curiosity. But before we dig into that, I would like you to tap into your story, and I would love to hear it in your own words. How did you come to where you are today? How do you remember yourself as a child? How did you get so curious about, even before biology? I know you were, you have background in programming and information theories. Link these pieces of knowledge for us and tell us your story.
Yeah, well, thanks for having me. I had an odd background, I suppose, and I actually got started, in computing, and I'd been writing code since I was 8. Like I got into computers really early, and I had no real interest in biology back then. Actually, I took a couple classes in it, didn't really like it, and I think as aside, a lot of sciences and secondary education are taught very poorly by people who don't really like science, which is it's hard to inspire a bunch of young minds if you don't know or like the material. But it wasn't until later that I got interested in it, and so I had kind of run down that path for a while and did some work, everything from kind of programming to cybersecurity and network type stuff, mobile application development. And I got really into biology with kind of an odd question, and I got curious about how immune memory worked, and this idea that if you get a vaccine or catch a virus, something, your body can build a memory to it, and in a disease that could have once been lethal won't even give you the sniffles. Really, it can be very profoundly effective. And but as a computer scientist, I was wondering, where's the file? Where's the hard drive? What language is immune memory written in? And it's this thing that we take for granted. And it led me down a rabbit hole into the world of immunology. And I got interested beyond just like the idea of this long-term memory into things that were really hard to vaccinate against, HIV in particular. And how, you have tens of millions of people have died from HIV, and a handful of them made antibodies that kept them safe, though. So they either didn't get sick or got sick very slowly. And we've pulled these antibodies out of the arms of survivors, primarily in Africa, these elite suppressors or elite controllers. And so we know the sequence, but if you think about this from more information theory point of view, basically waged a brute force attack against a password with flesh and blood. So every person who caught it made countless trillions of antibodies and eventually succumbed. But this handful of lucky ones made an antibody that bound to the virus in a way it couldn't escape. And no one had been able to really successfully elicit those with the vaccine. And so I was interested, though, in kind of abstracting this process to password crackers, to FPGAs. And so I wanted to try to wage a war against a virus with the computational power of the planet instead of the souls of people. And as I went down this path, learning about the variable regions of B cell receptors and how the cells actually would create these things, some scientists pointed out that cells don't have USB ports and you can't program them. Even if we have the sequence like we do from the elite controllers, we can't just upload it. And as a computer scientist, this shocked me. I thought that for sure someone would have solved that problem. And it's kind of speaking to my ignorance of the field at the time. But people wanted to mess with DNA ever since they knew what it was. But no one had a great tool to do it. And so I said, well, I want to build an app store for the human body, immune system software. And that's where the name Immusoft came from.
This is so cool.
So portmanteau of those words. Yeah. And so we set out on a mission to basically engineer B cells to produce autologous long-lived plasma cells that secreted therapeutics.
So this is awesome. I want to ask you more about the information theory of DNA and your views on it. How, I don't know, when you go hiking and you sit around the fire and look at the night sky, like, what do you think about? How do you think about how to even maybe deal with genetic diseases? Is it only information? What are your views on the information theory of aging, since you're also in the longevity field?
Well, the North Star that's taken me into the field of biology has been that the essence of life is information, not chemistry. Chemistry is a substrate. But just like, you can't learn much about your iPhone by looking at its silicon. Like it's the software on it that makes it do what it does. And so of course the substrate matters. And if you break it,
Mm-hmm.
you throw your iPhone off a building, it won't work anymore. And so but the software is what's defining it. And I think that your DNA is something analogous to this, or maybe firmware if you wanted to be a little more precise. But I think if you look at genetic diseases specifically, humans have a remarkable resilience to genetic damage. You can break a lot of things and not really notice a difference, or at least not for a very long time. There are a few places where there's no tolerance for this, though, or you can have a single letter of your genome is different and it'll be lethal, or you'll be in really bad shape. And in some respects, those are conceptually very easy to fix, but practically it's quite difficult. Of course, your body has a vested interest in not letting you manipulate the DNA, and it likes to put up a fight. But Immusoft's first treatment that's gone to clinic was for a rare genetic disease, MPS1, and that in this case, it's not actually correcting the genetic defect like in the genome. It's not like fixing the broken Aegis. It's just giving them a new copy of the gene, and so it's replacing it in a different location, and that's necessary for various engineering reasons. You need to be able to do this efficiently and reliably at a large enough scale. And as we built it, there weren't tools to modify it across the body at a high enough efficiency. But I think it's kind of like a holy grail of sorts in genetic medicine to be able to manipulate, the genome of every cell in your body. It's, probably from a practical point of view, won't be possible, but you can. The higher we get that efficiency up, the more we can do with these tools.
Let's talk about that in a little more detail. I want to get back to your approach, and I want you to finish whatever you wanted to say, but the approach of the B cell reprogramming versus the approach of AAV-based gene delivery for this specific example of MPS1. And if you could tell just very briefly to our audience the MPS1 disease, the mucopolysaccharidosis type 1, and just describe what the limitations are there, what the patients are experiencing, and how would you compare this B cell reprogramming approach to the more traditional, which some other companies are developing by delivering gene via an AAV vector?
The case of MPS1, so this is a lysosomal storage disease, and it's lysosomes an organelle in your cell. You can think of it kind of like a little stomach for the cell. It's full of powerful enzymes, and it breaks down things that go into it for recycling purposes primarily. And it's full of a whole bunch of these different enzymes as specialized purposes. And if you're missing any of those, whatever it is that they're supposed to break down still goes to the lysosome, but it can't be removed. So it accumulates there. And it causes catastrophic dysfunction. Like the disease untreated is lethal in childhood. And it affects pretty much every kind of system in your body, from skeleton to muscle to brain. Like it's really nasty. And the standard of care for it, in the US at least, is to get a bone marrow transplant or a hematopoietic stem cell transplant when you are quite young, like a couple of years old. And this makes a big difference. It can, probably double the lifespan of the child. They can make it into early adulthood usually with that. But the treatment itself has, considerable morbidity and mortality, like giving a toddler myeloablative chemotherapy and a cell transplant is really hard on them. And so it's not curative. They still will have, surgeries throughout their life. They won't, grow to full function, but it will kind of arrest the cognitive decline substantially, and it helps. There's also a recombinant version of the enzyme. It's manufactured, and it's administered as a IV infusion once a week typically. But it's very expensive, hundreds of thousands of dollars, and the enzyme has a very short half-life, and so it will they try to just saturate your liver so it can't consume it all, and then get it to other tissues in your body for 3 hours sitting there taking an infusion, and then by the time you go home, it's basically already out of your bloodstream. And so they hope just enough of it got into the lysosomes to get you through another week. And so none of these things are curative by a long shot, but the standard of care has been improving over the years. And so what we're doing is basically reprogramming their immune system to make this enzyme. And the idea is that you have this subset of lymphocyte of B cells called a long-lived plasma cell. And a plasma cell is effectively a specialized factory. And it's one of the most prolific secretory cells in the body. A mature one can make between 10 and 100,000 antibodies a second. So it's like parallel processing and manufacturing on an unimaginable scale. And you've got, millions and millions of these things. And so there's enough, in fact, immunoglobulin in your blood that if you took it out and spun it, you could actually see it. Like there's grams of it. And you couldn't see it if you lost all your blood, but there's a lot of it in there, and so these cells produce the bulk of it. I mean, if you you take the blood of an 80-year-old, you can still find antibodies against smallpox being made by the same cells that started making them all those years ago. And so the thought was that this is, in some respects, a really perfect manufacturing system. And it's able to do this for decades on end and it survives. So it's really quite remarkable. They can produce all sorts of things. Like we're making them secrete enzymes right now, but we've made them produce even things like collagens, like all sorts of weird proteins that you wouldn't expect a lymphocyte to make. And they just have really good machinery for this. And there's another interesting wrinkle to them in that most plasma cells you'd find in your blood are short-lived. They live for a couple of weeks, basically. And they die from endoplastic reticulum stress. They're basically making so much stuff that it wears them out and they die. And what's weird, though, is that if you get one of those cells into a survival niche, or primarily in your bone marrow, then they're effectively immortal. They can keep this up forever. And they like strap themselves in. And I don't know exactly what on earth is giving them this ability. Like we've played with this a bunch, but I mean, there's a lot of transcription factors you can identify and stimulatory factors. But if you knock it out of that niche, even if it's like a 50-year-old cell, it'll still die in a couple of weeks. So they're conditionally immortal based on their environment, and they even lose their B cell receptors, so they can't even see what they're responding to anymore. Just their gas pedals are glued to the floor, and they're cranking the stuff out. And so the idea of using these things to produce enzymes or other things that you want a steady level of for a long period of time is really attractive. And since we're modifying the cells outside of the body and they're in an environment that's more tolerogenic than anything else, I think you can load in lots of stuff to them and they can stably express this and ideally not get themselves killed. And there's I think if you look at the AAV vectors, I mean, they have pros and cons for different applications, but I mean, of course, they're immunogenic.
Mm-hmm.
Your body doesn't like viruses; it knows that they are. There's been viruses waging war on life ever since life existed, as far as we know, and it has exquisite defenses against it. And so you can typically only do them once, and the AAV in particular have a pretty limited payload capacity. So when you start putting in larger genes, it becomes difficult. I think there's applications like the eye and to some extent like in the CNS where the tropism of it is attractive if you're for certain applications, but delivery really is the Achilles heel of genetic medicine. And ironically, it's something that like led to the formation of Oisín and Sigma as well, and that developed a professional obsession of sorts of this, that from the time we started wanting to build this app store, saying, okay, well, how do you modify a B cell? Because the standard tool back then was like use a lentivirus, so it's a VSVG lenti, and B cells are largely refractory to it. They can't be transducible. And so we eventually figured out how to make that work, but it wasn't easy. And in the early days, we actually put the shell of measles on the core of HIV. So it's measles pseudotype lentivirus and use that to get in. And that's like makes it vastly more infectious. And so, but that virus is difficult to make. It kills its producer cells like crazy. So the titers are always lousy. And so this kind of journey went through from measles pseudotype lenti to VSVG lenti, and then eventually to electroporation and this thing called the Sleeping Beauty transposon system. It's a non-viral way of loading the cells. And with Oisín, we're using this thing called the proteo-lipid vehicle, which is built to be, it's more of a competitor to AAV.
Let's just stop here for because I do want to get into this in more detail with Oisín and your approach, and as well get back to information theory of aging and longevity. But just to dig into the approach with B cell reprogramming. So have you used CRISPR for B cell reprogramming, or is it on the table?
No, well, so we looked at this really early. Like I was actually remarking to a friend of mine down in Doudna's lab. Gosh, it'd be more than a decade ago or something. It was early on when like CRISPR seemed cool, but long before Nobel Prizes and all this crazy stuff going on. But we ended up not using it. I like ZFN too, actually, and Talons are two other ones we looked at. But the issue with them at the time, and I think probably now as well, although it's improved, is that they're not that efficient at larger inserts. And so if you're with the Immusoft's approach, you like take these cells out of the body, you modify them, grow them, put them back, and so you have to be able to modify them like stably, or like integrate this construct reliably in millions of cells. And when you're looking at an insert efficiency with some of those CRISPRs at a like call it a 5 kb insert or something, like it's so inefficient that you can't actually make a viable therapy with it. And so I think especially then it was really useful as a research tool because of how quickly you could make them, but it didn't have it wasn't practically useful for what we wanted to do. And I think now you're starting to see CRISPRs go into clinic, and I think they've gotten better in reducing things like indels and all that kind of stuff too. But at the time it just wasn't efficient enough, and that's why we end up with the transposon
And
instead.
so tell me about the transposon system. So I don't think I've ever used it actually, but from my memory, it kind of inserts into the DNA just kind of like a lentivirus would, but it does it at a random location. So is there any danger with that?
Yeah. So there's different
Mhm.
kinds of transposons, both endogenous ones that we have in our genome now and engineered ones, and even different flavors of Sleeping Beauty, and they have different characteristics. But the Sleeping Beauty one specifically was recovered from a fossil gene in a
Hmm.
salmon. So it's computationally resurrected from evolutionary sleep. That's how they got that name by actually some guys who were very interested in computation in biology, but back in early days before my time. And so these guys at University of Minnesota, Perry Hackett and Scott McIver, and all them were working on this stuff. And so it can be thought of kind of as a cut and paste program in biology. So it can grab DNA from one spot and move it to another. And the transposons themselves are like little DNA sequences, and you've got hundreds of thousands of them in your genome. Think of them as like kind of anchors or little pegs in there. And the transposase is actually what we are referring to with this system, and it actually is an enzyme that will grab two of these and cut out what's in the middle and move it around. And so there are no cut and paste transposons active in humans today. In fact, I don't think there's any active in any advanced life today. But they and for reasons that probably seem obvious, that it could shuffle your chromosomes like a deck of cards if you just left it on all the time. It's just cutting and pasting random things. And random tidbit, heard that the estimated time it was last active in nature was during the Cambrian explosion, which is kind of a fascinating little bit, and you wonder how this life appeared in such a short period of time, and maybe there is some serious rearranging of genomes going on. But so this enzyme has some benefits in that it can do these larger inserts more efficiently, and it's as close to true random as you can get because the distribution of transposons across your genome. And that might initially sound like a bad thing, but so most of your genome isn't coding for proteins or things like that. And the worst kind of behavior is probably from things like the gamma retroviral vectors. They look random, but they actually have a preference for areas right before genes, and so those are regulatory regions typically. And so they're in fact the first real big splash made in gene therapy was this for like XSCID, right? It's like a boy in the bubble type of disease in children. They were modifying their cells with gamma retrovirus, and it's a really fascinating bit of history that I think kind of should inform what we're up to today. In that, so this disease was 100% lethal. You had no functioning immune system. Kids would always die. They gave them this treatment, and they were able to restore a functioning immune system in the kids. But it gave, I think, a quarter of them cancer, and a couple of them died from it. And this, in one sense, should have been thought of as like an absolute remarkable success. You went from 100% lethal to 10 or 20%
Right.
lethal.
Incredible.
That's amazing. But that's not how it was perceived. All that made the news really was that they gave kids cancer with this gene therapy, and so it set the field back quite a bit. It was it's a massive. It's why any integrating therapy, you still have to follow patients out for years now, and I think it's 20 years in the U.S., I believe. and so it's a long time. And but I think it's worth considering this when you think of the perception, like saving 80% of people should have been, like, they should be having a parade down, like Times Square for this. But no one was focusing on that. It really was the fact that these they give kids cancer, and that was just, no one was expecting it. Now you look at like CAR T and stuff like that, those treatments have killed a bunch of people, and the FDA is scrutinizing it now for the risk of oncogenesis. But I think the public mindset has adjusted to some extent on this. And also these are, adults primarily, or people who have cancer. They know they're, in bad shape. And so I think that that's played a role in this. But it's something I think we should consider as we look at going to longevity and things like this. If you could work, 99% of the time or 99.99% of the time, and if that last sliver has something really bad happen to them, it's not going to be a good for the space.
So do you have any thoughts on, just a little bit off track, but apparently the human DNA has something like 40% of retroviral DNA in it. Do you have any thoughts of why the evolution preferred to just leave it in there?
I've usually heard like a smaller percentage cited for it, but I think that the idea of in some respects being a endogenous retrovirus is a great win if you're the virus, right? You can get into like
Good for the virus.
the creature and then all their progeny forever. But humans and every living thing's under a constant state of change and pressures from their environment and randomly mutating. And so I think that if you have a virus that successfully integrates but impairs function, that there's going to be pressure to remove it, even if your body might not be actively attempting to destroy it, but if it's causing some harm, it's going to get broken. And so you end up with basically mutations that disable it and leave the detritus there, because if the detritus isn't causing trouble, there's not like much impetus to get rid of it. And so I think that's they find their way in, and they get picked off at some point for causing trouble. There are some that are still human endogenous retroviruses that are still actually functional, and I think they're kind of fascinating. Like they'll like become active at some point in your life, like in embryogenesis,
That's
and
right.
then shut down again. And the general thought's that they must provide some benefit, or they would have maybe it's a resistance to other viruses, or and I mean a lot of this stuff gets very speculative. Right. But yeah, we know that in general there's pressure to get rid of things that are bad, and so that I think that explains how they get broken. How it sticks around for that long is a kind of another, that's a different question. I don't think we really know what it's doing.
Well, now maybe with the genetic editing tools, we could just cut them out and see what happens. Like if
yeah. I mean, there is a lot of work for. So the work being done to engineer pigs for human organ transplant, right? So that pigs about the right size to donate an organ to a person, and but one of the big things that, other than like HLA in general, immune matching that had to be changed, was the fact the pig has a bunch of endogenous retroviruses also, and there is a big concern that those might be really bad for a human.
I think that was the reason that the transplant didn't work the first time, because there was a year ago, there was a surgery of the first transplant for a cardiac patient of the pig heart, who unfortunately died later, a few months later, and I think this was the reason.
Yeah, if you have any of those things were not taken out entirely and they reactivate, your immune system is going to go bonkers. And it's already tough to keep it like balance, this art of having an immune system with this foreign tissue. And so a lot of work went into deleting those. So no one's tried to delete them from a human, but certainly in animals for this purpose, they've taken great pains to remove them. And I think, in that case, they didn't get them all, but and it's I guess it's kind of an interesting question of how do you know for sure you've got them all. Like there's certain patterns that make viruses look obvious, and so you kind of scan for them and remove them. But if one evades it, the question is how did it evade the detection, and what are we looking for? All the things we should be looking for.
So let's go back to the B cell reengineering. Just one last question I've had is around biodistribution, because you were saying that the viruses like AAV vectors could be attractive for some of the central nervous system, brain, or eye disorders because of their tropism, and as well as in comparison to the B cell reengineering. So, what are the limitations there, considering that the brain is somewhat immunoprotected, so that I don't exactly know like whether it could be useful for brain disorders or not to reengineer B cells.
Yeah, yeah, no, it's a great question. And so in the case of, you think of like most in vivo gene therapies out there are supposed to target the liver because it's
Mm-hmm.
easy to hit. So, and there's of course AVs that the liver very well as well. But the interesting thing about a B cell though is that it's a living thing, and so it's capable of chemotaxis. And to be more precise, we don't put back plasma cell, we put back a plasma
Mm-hmm.
blast. So it's the immediate precursor to a plasma cell. And the distinction that's relevant for this purpose is that the plasma blasts are migratory. They have a chemokine homing receptor and can home. So that the body kind of one way it regulates cell trafficking is by leaving kind of like chemical gradients, like you have like a little breadcrumb trail cells can follow. And so there's different like sources of these emanations from different tissues. And if a cell wants to go somewhere, it can, upregulate a receptor for that thing, and it will just migrate up the stream until it gets to the source. And so the plasma blasts migrate to survival niches. That's in their nature to do it, and they need to have that. It's why, like, if you knock a long-lived one out after all the years, it can't get back in because the fully mature one doesn't have that ability. And so it's capable. It's possible though to manipulate the migratory aspects of the cells. So like you could make them go to other tissues, and that's something that like people do a lot of engineering of viral capsids and stuff to try to affect their tropism. But cells that naturally run through the blood have we know this machinery pretty well, and so I think if you could cause them to go elsewhere, and they'll naturally also go to sites of
Mm-hmm.
inflammation. So it's kind of an interesting thought for something like MS, where you have if you have an infection in the brain or inflammation in the brain, immune cells can traffic up there. The barriers open up, but also in cases like rheumatoid arthritis, where you could, in theory, attract a cell that has something to shut down that inflammation, but once it did that, the niche would probably go away too. And so you have the cells that were there would no longer have the thing that kept them alive. They would go away when the treatment wasn't needed, which could be a kind of an interesting dynamic. But it's one we haven't done a lot of testing on. Although I think when you're modifying a cell ex vivo, you're relying on its behavior, and usually because you want it to go somewhere or likes to go somewhere on its own. Whereas the viruses, you think usually a very small percentage of the virus that you put into a person ever gets to the intended destination. It's the liver, unless that destination is the liver, in which case lots of it goes there. It takes up
Well,
almost all
unless
of
it
it.
is like a very targeted delivery. So I previously worked into delivery through the brain surgery, where a very small amount of virus is put into a specific brain structure, and then the biodistribution is kind of like
Yeah.
specific to that region.
Well, it's weird about that. Yeah. So the viruses, yeah, and local administration tend to uh, stay local, but the things like LMPs don't actually. Like, if you inject an LMP into your brain, like through the skull, it'll still mostly be in the liver in 24 hours. It
Right.
tracks actively out. It's those things they're really weird actually. I'm not quite sure why they're so they love to traffic the way they do. But you can pretty much put those things anywhere and they'll end up in the liver. And it's really it's kind of funny to watch it. You're just like, wow, you're like, put it there and you can watch it go with like in vivo imaging and stuff, and see it the liver's lit up in 24 hours. But yeah, so the viruses you can control them based on like where you put them. And I think that's why like applications in the CNS and the eye were things that were attractive early on with them. Also, in places like the eye, you need way less virus, and a virus is very expensive. So it was kind of a practical,
Mm-hmm.
logical
And so,
place to
from the
start.
clinical trial standpoint, I know recently there was some news about the B cell reengineering therapy for MPS1. Could you just mention a couple words about that?
So it's a phase one on the safety study primarily, and they're collecting, of course, all the information they can on that. But I don't have a readout for it yet. It's only
I
a few months
see.
ago.
But does it seem
But
to be safe so
um,
far?
I yeah, as far as I know, everything is well tolerated. There's no adverse reactions to it, so that's everyone's excited about that. But and I mean now it's like I said, it's the first of its kind, first engineered B cell therapy to ever go into a human, and moving through the we pushing up the dose, going through more patients and all this stuff. And but it seemed to be flawless from that. Like nothing. I mean, you didn't need to have any conditioning or anything like that. So it has like a lot of benefits for compared to doing either viral therapy or a stem cell therapy. So
Mm-hmm.
but I sadly do not have the data
Well, but
yet from
that's
it. But
exciting. It'll be exciting
everyone's excited about
to
it.
see the readout. So let's move now. Let's transition from the Immusoft to Oisín and to longevity, from rare diseases to longevity. So let's get back to the question about your views on the information theory of aging and how does it tie into, again, your approaches and what you choose to do with this new biotech, Oisín Bio or Sigma Genetics.
Yeah. Well, I mean, a lot of this comes back to the same, North Star that I had from, 15 years ago about, information in life. But in the case of aging versus a genetic disease, like you do develop, like somatic mosaicism as you age. You take mutations and things like this. But I think in many respects, it's not so much the genomic damage that's causing trouble as much as it is the dysregulation of what code is running. And so I mean, certainly if you can't maintain the fidelity of your genome, you're toast, right? Like it will set this theoretical limit on life. And you can certainly see a difference in longevity in species that have really effective DNA repair systems and ones that have less effective versions. And so I think this definitely it's a big deal on even the mutation level. But if you look at you know, think of like you don't get a wrinkle because your body forgot how to make collagen. Like you still have the gene sequence for
Mm-hmm.
collagen there, and maybe some of the cells got damaged, but there's still like there's enough there you'd be able to do this. You don't have like epidermolysis bullosa or something, and so what you're ending up with is in the case of senescent cells that impair regeneration because they have this inflammatory secretory profile that impairs regeneration, or you have just an epigenetic changes to the cells that prevent this behavior. It's a little different than a more traditional genetic disease, and I think one of the most interesting paradoxes in biology, in my mind, is this kind of paradox of mortal humans with immortal germlines, and
Mm-hmm.
that like you can take the oldest sperm and the oldest egg you can find, put them together, in a few days it's 0 years old. It resets itself back to the beginning, and that's pretty interesting, especially from like the computer science lens, because it suggests that there has to be some kind of backup of the epigenetic state. Like there has to be some copy that it goes back to that says, oh, you're supposed to like methylate or demethylate this thing or rearrange your chromatin structure that way. Like, and I mean, if it didn't, obviously we would be born old and we'd be extinct. We'd die pretty quick. But somewhere buried in the source code of every nucleated cell in your body is a program to undo age, and I think that's a really fascinating thing. And it's one that people are trying to harness now when you think of like the epigenetic partial reprogramming and all this kind of stuff. And from the time the Yamanaka factors were discovered, this kind of inspired people that you could maybe pulse a cell back to a younger state without losing its identity. And so this, I think lines up real well with the like information theory and aging. But you also have other things that shouldn't be ignored, like the accumulation of extracellular damage,
Mm-hmm.
which is just pure protein junk that your body can't break down. Think of like certain kinds of cross-links or your like oxidized cholesterols and stuff, and where you actually don't have the proper tools in your body to break that stuff down, because I guess there wasn't a need maybe to make it, because so many things would kill us first that it never really was an issue until we started pushing the average lifespan up so much. And so in that case, I mean, you could look at it through the lens of information, and you're going to need to give the body new code, but it's not so much that it's dysregulating something that it has already. It's that it simply doesn't have the ability to repair that kind of damage. And this, I mean, I think is it really. We've roughly doubled the average human lifespan in the last 100 years. But we did that entirely by changing the environment. Things like starvation, predation, infectious disease. We've become more peaceful, despite what it might look like if you watch the news. But if we want to double the human lifespan again, we're not going to be able to do it through the environment. We're going to have to do it by changing human. And given that we're the second longest lived mammal on Earth, it's not actually really easy. Like, we have pretty much every dirty trick in the genetic playbook wired into us. Like, I mean, we live more than twice as long as our nearest kind of like primate relatives. And so how do you improve upon a creature that is this long lived with this high of metabolic requirements? And it's, I think, one of the more interesting things out in the field. Like, how are we going to mess with this code to go beyond what it initially was doing?
Mm-hmm. And so how does it tie in with approach of Oisín Bio to target senolytic or senescent cells with senolytic gene therapy?
Yeah, so when we got started, I suppose, like a bunch of the field, we were excited by that, study done at the Mayo Clinic in the Buck, where they use those transgenic mice to ablate P16 positive cells, and showed that by removing these across the body, you could have significant improvements in lifespan, but also in health span. If you did this, particularly starting when they were young, most of the pathologies of age just didn't manifest themselves at all. And the problem, of course, is that you can't go back in time and modify your own embryo. So it's like purely academic. But when I saw it, we started thinking, how can we build a version that would be translatable or clinically viable? And that's what led to us using the PLV technology and saying, okay, we want to deliver this payload to the goal, hit every cell in the body, like as much as we can, and we want to just remove the senescent cells. And the idea behind the senolytic is pretty straightforward, that normally if you damage a cell, like, it either fixes itself or kills itself or gets killed. But it's possible to damage them in a way that it can't do those things. And so it sits there jammed in irreversible cell cycle arrest, unable to like live or die properly, basically. And they start secreting inflammatory cocktail that should recruit an immune cell to get them killed. But as you age, like, the kind of immunological noise basically goes up to the point that, like, you get inefficient at clearing them, and then they start accumulating exponentially. And so these things are just impairing your latent potential for regeneration. And so the idea is, if you remove them, you don't alter the theoretical lifespan of the organism, but you remove junk that's impairing its function. And so it seemed pretty straightforward. And in some respects, we're thinking of it as kind of low-hanging fruit, technically, with the approach we were using. And I think in some respects we were right about this. So we got good at this pretty quick, but it's not as straightforward on a regulatory lens, actually, in that, like, I think it's generally accepted that the accumulation of senescent cells with age is deleterious, but like tying the removal of them to a specific population, a specific endpoint for like a phase 3 trial is not as straightforward. And with some of the early failures in the space, I think it's given people pause on it. And so I mean, it's not our lead program anymore, partly because of that, and partly because there's large pharma interest in like the muscle building and the fat killing programs. But I still think it's a good thing to do, and it's likely one of those things that would buy you a few more years of health and functional lifespan. Like, I think it really is something that needs to happen, and we need to figure out a good regulatory path that would allow it to get into clinic and eventually be more broadly adopted.
So what do you think could help to bring this into clinical trials and to bring this to FDA approval? Does FDA need more preclinical data, or just to change mind about even fundamental viewing of aging and disease?
Yeah, well, I mean, there's, I suppose, a couple different perspectives on this. I, we're operating like any other biotech would, and although I'm very passionate about longevity, and we want to build treatments for all this, and have a very long time horizon where we want to keep building these for a long time. In the short term, you still have to make a drug that you can get on label, that the FDA thinks is a disease, and that you can ideally license to a big pharma or something like that to just be a successful entity, company that makes these things, and gain the resources you need to tackle the big problems. And I think that it's hard to tackle things as monumental as aging without big resources. And I mean, it's hard to rival the resources of a big pharma. You have $100 billion a year in revenue. It's so that's a lot to be bringing to bear against a disease or a mechanism. And so, but from our point of view, like I said, we're kind of looking at, okay, well, in the case of senolytics, we were looking at blocking the transition from acute kidney injury to chronic kidney disease. You have a unmet need here, and we think senescence is believed to play a role in this kind of vicious feedback loop that drives the kidney into failure in the end. But from just an acute point in time injury to like a chronic one. But the models for that are difficult in the mice, these ischemic reperfusion injury models. And I think the osteoarthritis actually is a good model and would likely work fairly well for the treatment we built, although particularly after the Unity trial, I think that there wasn't a lot of appetite in the investor community to go after it again, even though the trial failed for things that were kind of largely irrelevant, in the sense that you need a systemic, I think, administration of a senolytic to be effective. I don't think doing it locally in that case was going to work based on the preclinical data for it. But these are the kinds of things that people have been looking at. Like, how do you just choose a disease and ignore the fact that it's a senolytic and you could use it for aging and you have all these grand things? Can you just show it works in a patient population where you don't have to do anything revolutionary, just the normal kind of FDA path? And I do think that the regulatory environment will likely change, that we'll start seeing the benefit of going after like constellation endpoints for things that affect multiple systems. But it's tough, and I don't think it's so much that the FDA is unwilling to consider it. It's that you need to figure out how do you show them that it works. Like, how do you kind of put that together? We can't do lifespan studies in humans, unless you're in really bad shape, not for healthy ones. And so that looking for good biomarkers or looking for other endpoints that you can show. If you can show a treatment is safe, that first of all, it can be used off label, but also it's a lot easier to say we want to try it in a different population if you already showed that it didn't cause harm in the first one that had the clear need for it. And so I think that, like, you look at Ozempic's a really good example of this, or semaglutide, the GLP-1 agonists in general, that I think these might become some of the first broadly adopted health span improving drugs out there. And but they got started in diabetes, and when people figured out they were useful for weight loss, the off-label use just exploded. But what they started to see later in these trials is that you're getting cardiovascular improvements, reduction in cancer, like that. I mean, something that's on one hand fairly obvious. People in the developed world get old, they get fat, they get inflamed, and bad things happen. And if you can remove that, it's not much different theoretically from the senolytic in that respect. You have a whole bunch of cells that are stirring up trouble. In this case, just because you're obese, but the removal of things like the visceral fat in particular, I think, were big benefits. And so I think it took a few years before it got approved for weight loss after it was approved for diabetes. And I think the idea of saying, could it get approved for reduction in risk of cancer or reduction in risk of cardiovascular events? I think there's a case to be made for this. And at some point you look at the master corollary for pretty much every bad thing that befalls humans is age. This is the dominant risk factor, and so pretty much any disease you can think of. And so it's not a stretch to start pushing it to say, okay, well, if you're old and you have X, or if you're old and you have Y, like you kind of like you can envision a path forward that doesn't involve a real revolution on a regulatory landscape, just incremental change. And I mean, I think the other thing, of course, is that there's going to be jurisdictions that start allowing more aggressive things, and if things work, then there'll be pressure for the bigger ones to come along, and if they go horribly wrong, then I suppose that will have a bad effect on the larger ones too. But
I heard you describe this before, the approach itself, and it also ties in nicely into the information theory of life, of DNA. When you describe this senolytic therapy as a program, if you damaged, kill yourself. So I thought it was just such a smart
yeah.
approach. Do you think could this approach be used in, let's just say, maybe not in a cell as a whole, not in a damaged cell, but perhaps in a protein when it aggregates for some types of aggregate diseases like amyloids, different types of amyloidosis? Is there any way how this approach could be used in order to remove the amyloids?
Well, not directly in the sense of like Boolean logic in DNA requires, a nucleus and transcription factors and things that can like interpret it. And a protein aggregate doesn't have those things. But I think that you could use it to basically say you had an enzyme or a protein that broke down a plaque or a crosslink. You could use a tool like ours to cause cells nearby to secrete it and break that thing up. I mean, one of the ideas that I was keen on really early on was to, in the case of the oxidized cholesterol, SENS had those enzymes that they're bacterial, I believe, that could break down the oxidized cholesterols that humans couldn't. But if you just inject a bacterial enzyme into your veins, it's probably not going to go super well. Your body's going to dislike this. But the thought was, what if you made a macrophage express it? And then the macrophage, it might get itself killed sooner or later, like by MHC presentation of it, but it's going to naturally traffic to those plaques, and now when it munches them up, it's not going to die as a foam cell or become a part of the problem. It's going to actually be able to break it down, and you could just keep administering this and hitting just the macrophage, and even if your body at some point became like resistant to the macrophages doing this, or like you developed an immune response against it, you could still probably argue that maybe just brief transient suppression of your immune system to remove that plaque would be a worthwhile trade-off. And because it doesn't have to be there forever, it just need there to damage repair for a point in time. And so I think those kinds of approaches could be used with the tools that we're building. But you do need something that's capable of removing your target protein. Like the cross-link breaker is a really tough one. It's on my mind a bunch. I know there's at least one lab that has been working on it, but and I'm sure others. There's fields growing all the time, but it's been relatively obscure, and whereas the plaques gotten more attention. But yeah, if you have something that will break it down, you can make it as a transient or a permanent gene therapy, and have like it expressed where it needs to be. And I think that's kind of where we start getting at this. You're going to have to improve the human if you want to live longer. And I mean, actually a really simple example that's straightforward enough, at least in theory, is the APOA1 Milano variant. I don't know if you're familiar with this, but it was basically a mutated version of apolipoprotein that was found naturally in a village outside of Milan. And what I find slightly amusing about the whole story is that someone there had to think that those people should all be dead, and curious why they're still alive. Like, I don't know how bad their lifestyle was. That like a visiting scientist is like, like how come you guys look in such good shape? You just all you do is eat and drink.
It's all this variant.
Yeah. It was. I don't know. I've never met the people who discovered it, but you got to think of like how on earth why would you ever look like what made them decide that those people like must have something really crazy going on but this is a gene that we all have, just like a small mutation to it that makes it a lot better at reverse lipid transport, And so these guys would basically never get cardiovascular disease. They were incredibly resistant to it. And so there is a company that was trying to do this for a while, and I don't know what became of them actually, but where they are making this recombinantly as a drug. But you could think of using this as a
Hmm.
gene therapy, where you just say, I'm going to inject you with this once, and you're going to still make normal apolipoprotein, but now you're going to make this high power variant also, and it's going to like be a lot more effective than the one you normally have in that. But it's effectively a fully human gene, which is what one of will change. So hopefully your immune system doesn't get mad about it, and and it can do its job long term. And then you have like basically a prophylactic gene therapy for heart disease. You know, it actually like seems like a no-brainer until you start contemplating what the clinical trial and endpoints are going to look like. And then you're like, oh, actually, that seems much harder than
I know.
you have to make a lot of it for a long period of time to see statistical difference over a large patient population.
So, what do you think about would this be possible to be used off label? I can imagine some, people who really, really want to use it and who don't maybe care so much of it being FDA approved. I can imagine companies maybe popping up under the table trying to deliver this.
Well, I mean, there is a big difference between those two things. So in the U.S., like a huge amount of the drugs are prescribed off-label. I mean, depending on the indication you're in, sometimes more than half the treatments are off-label. So like that's an integral part of the U.S. medical system, that once a drug is approved for something, it can be used for anything. It's up to the physician's discretion. Uh, Actually making something available like bootleg style that's either not approved at all or making a knockoff of it is a different beast for sure. And both them occur. Like but off-label use is like, yeah, it's a part and parcel of the medical system. Whereas the other one is a lot more fringe. And so you of course see this. I mean, a ton with just. I mean, there's kind of maybe a middle ground of like the importing a drug from say Canada or India or China, like where you're having a drug that's approved for something, but you're basically getting it from a provider that's not approved, or you're getting it in a chemical form that's not like it's formulated as like the drug substance, but not the drug product. And that's also fairly common, but less so than and it's not allowed like off-label uses. And the at least not really. There's a little. The importing of drugs is kind of a active point of policy right now. Like the state's trying to do it. I think Florida just signed off on it, and it's an interesting development. But when you start going into the further edges of like the real extreme biohacking, where someone's like, we're going to make a treatment, we're going to take it, and I mean that's on the far side of that spectrum, and I think it happens and will continue to happen. But I can't imagine it becoming mainstream in that like the risk tolerance of most people isn't high enough to do it. And there's an interesting thing about this. So like actually and a bit of a tangent, but it is relevant in some respects, in that the way Sigma came into being, the magnetoprator company, was I was trying to build an open source in vivo electroprator, a tool that would let you do gene therapy in the developing world or in the garage. It wouldn't require advanced infrastructure. And I did that because as I got into biology from computer science, one of the things that really jumped out at me is in computer science, like everything's like so much open source stuff. You can like mix and match, put your own thing together and roll with it. It's how like the internet really came to flourish, was like the first open source infrastructure for it. And but in biology, it's very different. In medicine, like the one person who has no power is the patient, right? Like the doctor won't prescribe it, your hose,
Hmm.
insurance won't cover it, her government
It's
doesn't
true.
cover it. Like if it's not approved, you're totally toast. And we're have this strange situation where like you can get a prescription to kill yourself in like half the states in the U.S. But you can't take an experimental treatment because it might hurt you.
Right.
And
It
that's an
doesn't make
odd
sense.
thing in my mind.
Double
And
standards.
and so I had wanted, yeah, it's just weird. It's a little like paternalistic, like protect you from yourself. Because I mean, if you have a disease and there's a pill you can take and it goes away, great. But like if you have something that's going to kill you and there's nothing that's even in animal studies for it right now, you're going to die like long before like that thing ever goes through like a primate trial, let alone into approval in a clinical trial. And so I think the current system kind of deprives people of agency, and it doesn't take into account risk versus reward. And that like a healthy person probably shouldn't just be making random molecules or changing around their DNA for fun. Like it's dangerous to do this. But if you have a terminal disease or like you know where things are going, like I mean, you should have a shot at it. So I wanted to shift the balance of power in medicine. That's why I was working on the open source electroporator, and it just took a very unpredicted technical turn when I paired up with my co-founder in that, Chris Peel. He is the CTO at Helion and the pulse power expert. I was trying to make it solar powered and kind of got over my head on electrical engineering. But so I got help from him, and he's like, "Why don't you use a magnetic field? That'd solve a bunch of problems." And I said, "Well, I can't build the simple one. Trying to build the hard one." And so he had put together his prototype, and we basically recruited a CEO and dropped off in Y Combinator. And it became like, and the new CEO, Zach Rapp is right now. It's taken an interesting turn again, where it started loading basically a sugar called trehalose into red blood cells, so let you freeze dry red blood. So it's a very interesting technical evolution, but that the whole origin of it was trying to build a device that could really kind of level the playing field in terms of biologic medicine with the patient. And like the first thing it built with it was Ebola antibodies. And so during that outbreak a few years ago, and there's limited supply of these things, and there's a clinic we're talking to in Monrovia that they are like, "Oh, we're gonna die, there's no treatment for this." And so I got the gene sequence for the antibodies from the CEO of the company that made them, and modified them to work in mammals, and built a prototype of this thing. And it never went into humans, but it really showed that you could take something that would normally cost $100,000 and make it for a
That's
few $100s
incredible.
of the DNA. And as a really cool project. And like I said, now it's become this company doing totally different things than we'd ever
So
imagined.
where do you see the future of this technology? Would you like to see it being taken?
Of the
Hmm.
magnetofreighter? Well, so the my goal for it initially was to make one big enough that you could put an entire person in, and so that you could basically inject a bunch of DNA wherever you want it to be, and then you like stand in this thing briefly, and it
Kind of
loads
like
it
a
up. But
cryotherapy.
I've been well, yeah, it's a little bit like going through an
Hmm.
MRI at Mach 2. So it's a soul crushingly powerful magnetic field that switches very, very fast. And so that induces a transient electric field across the cell, and it can move DNA and things like that into the cell. But the thought that you could use it in a whole organism is kind of where I was going with it. But I haven't even put my finger in that thing. And it's done most of its work in vitro, like making CAR T cell therapies, because it's way gentler on the cells, so it doesn't kill as many, but as let's say electroporation would. But the red blood cell thing is relatively new. It was kind of just someone asked if we could do it, and we're like, we'll find out. And the very first experiment ever done on it actually was we just put whole blood in it with DNA and zapped it, and we were able to transduce or transfect the PBMCs in whole blood, something that you can't do with electroporation. And so we just put DNA in, magnetoperated them, collected the PBMCs, threw them in culture, and just expressing GFP back then. But at the time, we weren't paying any attention to the red blood cells because they don't have nuclei anyway, so they can't read DNA. But we just know they didn't mess it up really bad, and that they appeared to still be intact. But so it was years later where the military had asked us if we could do it, and because being able to freeze dry blood could remove shortages in both the civilian world and make it so you can have blood where you just add water to it and you get blood in the austere environments in the battlefield and stuff.
So let's shift gears a little bit in the little time that we have. Um, Let's shift gears. Tell us a little bit about the follistatin gene therapy and some of the newer projects that you're working on.
Yeah, so the follistatin is this interesting one in that it's been we've known about this, or the field's known about it for a while, and it's been like something that pharma really went after for a bit, and it was like first kind of discovered, I guess, or the pathway was first found through the Belgian blue cow, which Google's like a super muscular cow. And it actually has a defect in a gene called myostatin, which is a negative regulator of muscle growth. So its typical phenotype is double the natural muscle mass of its wild type version or normal version. And the follistatin itself wasn't like discovered till later, but I think the first cow like that was documented in the late 1800s. But basically you can think of myostatin is a program your body runs that makes it as weak as possible. It's a negative regulator of muscle growth, and it's thought to primarily protect against starvation. Muscle's metabolically expensive, and so you want to be as weak as you can possibly be for your environment. But when the environment begins to hurt you when you exercise, then your muscles call for help. The liver hears them, and it makes this molecule called follistatin, which will take that break away and trigger muscle hypertrophy. And so, being the lazy scientist I am, I was like, well, what if you just jam it on 24/7? Then you can get super big. And this had been played with already in the lab before. Like it made like mice that were engineered to overexpress it that are huge. And there's been, like I said, a desire once follistatin was really found to try to use as a therapy. And the problem is that it has a very short half-life, so making it recombinantly is quite difficult. And it's also, and when they start making modifications to make it last longer, they become difficult to make. And so it had issues with that. And then there were a lot of people who were making just an antibody against myostatin, and some of those are still around, in fact, but they're not exactly follistatin, but they're kind of doing something similar. And finally, people actually made AAV-based gene therapies with follistatin for muscular dystrophy, where they just inject this into your muscle. But they all had real serious limitations that prevented them from really becoming therapies, and I think they largely had went away to some extent, and or at least had been relegated to the dark corners of development. And we want to use it for frailty though, and so you have a large patient population. The treatment can't be that expensive, and it has to be safe. And so in the case of AAV can make follistatin. You can do it with that vector, but it's a very expensive thing to do. And it was like in humans, I think it's only really been used in intramuscular administration, so not like a systemic one to make your whole body stronger, just local muscle. And it will be secreted from the muscle, but usually not at a level that would widely impact the rest of the body. And so the antibodies have not been super successful early on, but even assuming you get one that behaves really well, it's an expensive therapy to be giving to every old person out there who's frail. I mean, it's potentially millions and millions of people. And so the idea that you could use a non-integrating transient non-viral gene therapy would allow you in theory to take a shot of this once every few years and express a stable level of it. So I think like the technology that Oisín can bring to bear on it solves a lot of the problems. You no longer have CMC issues that you'd have making it recombinantly. You're not an antibody. You're making like actual follistatin, or you can tweak it to do optimize it for things, but it doesn't have the issues of like the FC region and different binding characteristics. And you're not using a virus, so you can repeat dose if you want or need to, and your cost of goods is a fraction of the price. So I think the stars line up really well for it in that respect. And so it's not a new idea, and that lots of people want to make follistatin for a long time, but I think we have a tool that can do it in a way that no one else can, and I think that's what gives it an edge, and I think that's why pharma is so interested in it.
And just to reiterate, this is the proteo-lipid vehicle, which is this novel technology. So the advantages are, of course, that immune system does not react to them, and the biodistribution is also seems to be really good, right? What are some other advantages?
Yeah,
Again, you
yeah,
could input, I guess, large cargoes that could go into the right places.
yeah. Large payload capacity. I mean, I think that those like the three that are probably the biggest: the biodistribution, the payload capacity, and it's like tolerability. Let's call it tolerability broadly. Like it's not immunogenic, so you can repeat dose, and it doesn't cause other toxicities like barbecue your liver
Hmm.
or something like that, like the LMP would. And so it opens the door. Like you start early on asking about CRISPR and stuff like that. And one thing that I think is fascinating of the idea of this is to use it with like a base editor,
Hmm.
and where since you can repeat dose now, you might not be able to hit like every cell in the body from a single dose of this, but you could just keep repeating it until you hit enough cells in the body that you actually made a disease go away. That's something that there's no other tool that can do that. It's really remarkable in terms of like what the potential being able to do like high doses repeatedly to hit tissues that are otherwise very difficult to get at. I mean, you can. The nice thing about it also is you can tune the distribution of it pretty well. You have once you took away the more toxic lipids in the LNP, the parameter space you could explore in lipid chemistry became much larger, and so you can really skew where they go quite a bit. And like we started saying, I wanted a flat biodistribution curve. I want to hit all the
Hmm.
cells uniformly, and but there's lots of applications where you don't want that at all. You want to skew it to a population, and so that's something that it can do, which I think is really
Yes, this is
exciting
such a
also.
great point, especially because redosing is such a big question with more and more gene therapies being developed using AAV vectors. But not only that, but even the initial dosing, because there's plenty of patients that already have been
Oh
exposed
yeah,
to AAVs and they cannot be dosed even with initial therapy.
yeah. I think this is a big issue with. I mean, one of the tragedies in the history of gene therapy, with the Jesse Gelsinger trial with the adenovirus. What's largely because in the animal studies they weren't their immune systems were a lot more
Hmm.
naive than a human who's been living for a couple decades, and so I think it is tough. Like when you look at the AAV serotypes, or even actually the adenovirus COVID vaccines, there's selecting the particular virus thereafter to based on North American exposure to it, and it's different if you live in Africa or something like that. Like the endemic viruses aren't the same everywhere in the world, and so that there's endless amounts of work that go into this. Like every year I go to ASGCT and it's like poster after poster of we're engineering an AAV capsid to make it redosable, or it's like every year's like a torrent of these things, and I think it's good to engineer the things. But
You
yeah,
just went around it and
the
came
first
up
year I
with
started,
a
I was like, oh,
much simpler solution.
yeah. I thought like the first year I saw all these things, I was like, oh wow, this looks promising. And it's like a
It
decade
still looks
later, I'm like, wow,
promising.
they're the same poster. But it's not
That's
easy.
funny.
I think
Yes,
is the point.
absolutely not easy. Well, Matt, I know you have to go. Thank you so much for joining the Gene Therapy Insights podcast. We've learned so much. Thank you for sharing all your incredible work and your story. And to end the podcast, I would like to ask you one last question. What excites you in the field? What excites you in science these days?
Oh gosh. Well, when we set out to, we started at Oisín, like we laid out like our strategy and field of where we want to operate with this stuff, with the kind of understanding that the science wasn't there yet for all of this stuff. That we thought that it would go in a certain direction, but we didn't know how to get there yet. We were kind of laying a foundation to do it. And so one of the things I think is just really exciting is how fast the field has grown, and this has gone from being kind of something that people viewed as crazy to something that's more broadly accepted. But I think it's just a more specific thing in the field. I think the marriage of like computer science and synthetic biology with medicine is it's something that will will shape the field going forward, and that like we're going to effectively take control of our genetic fate, and we're going to be harnessing the computational power of the planet to basically figure out the things that could not be figured out before. And so we're gaining insights into the world that like all the tools we use today like basically didn't exist a decade ago. It's really amazing. Like so the tools broadly and that one in particular, I think I'm really excited about.
Well, thank you so much. This is truly, truly exciting times, and it sounds futuristic, but it seems like the future is much closer to the present than we thought, and partly and largely because of people like you who move in the field forward. So I'm so pleased to have you on my podcast. Thank you so much again, and until next time.
Oh, thank you so much for having me. It's a wonderful time. Hope to do it again soon.
Thank you for tuning in to the GTI podcast. I hope you enjoyed the episode and found new insights for yourself. If you like the episode, please press like, subscribe on your favorite platform. Your best support will be sharing this episode with colleagues and friends. For the future content, comment below with suggestions of guests to interview and questions you would like to be answered.